So our second speaker of this morning today is Giovanni Pizzi. So Giovanni obtained his PhD in physics from Scuola Normale Superiore of Pisa in Italy. My accent was okay. He then moved to EPFL as a postdoc and then as a senior researcher. And since 2022, he's a group leader of the Materials, Software and Data Group at the Paul Scherrer Institute. So his research focuses on methods and application of high-throughput atomistic simulation for material design and discovery. And he's also a project leader of the Open Digital Infrastructure pillar of the NCCR Marvel. So today, he will give us an introduction on an open research data repository and reproducible workflow. And he will also focus on Material Cloud, that is a platform that he designed to enable open and seamless sharing of resources from computational science. Giovanni, thank you.
Thank you very much for the introduction and the invite. Can you hear me? Is it okay? Yeah, perfect. So today, exactly, I want to speak about these two topics, and I will use the examples of the platform we have been and the software we have been developing to make it a bit more concrete. But we'll try and understand also the audience is maybe not, actually probably most is not from my field. I'll try to show and mention where what I say is more general and can apply more broadly. And specifically, since it's a meeting between NCCR, as was already mentioned, I come from NCCR Marvel. Very briefly, I want to touch upon these topics, which I have a presenter here. First of all, I want to discuss, so in our research, we do hundreds of thousands of simulations, and I want to discuss how we manage those and we make it easy to then share them with colleagues and collaborators and with the public in general. And then we'll then move to the topic of data repositories, just briefly touching upon some differences within a couple of them. And then how, by combining this, we can achieve open science goals for simulations in the field of material science, and in general, in the field of simulations. And then I want to mention in the last couple of slides how we are also trying to address experiments which can be fully automated and try to combine them with fully automated simulations toward what are nowadays called autonomous laboratories, where artificial intelligence and machine learning algorithm can decide autonomously which next experiment to run or which next simulation to run in order to optimize a given property or characterize a material or any other similar research topic. So again, to explain where I come from and what we do is taking materials, and maybe can I stop it so I don't get, and putting them in a supercomputer and trying to predict properties for them. Okay, so we send them to the supercomputer. What we start from is really the position of atoms with methods which are called density functional theory. Whereas once you only know the positions of atoms, you can predict properties. We do it for typically inorganic crystals. I guess maybe some of you in the room would do it for molecules or something similar with quantum chemistry methods. And the goal is really, we have databases of experimentally known crystals where experimentalists do X-ray diffraction, and they know or provide databases of the positions of these atoms in different crystals. And the question is, can we find a better material for a given property? Do we want to get a better thermoelectric material? We want to get a better piezoelectric material. Is there anyone we know that we can find which is better than anyone known and has no maybe toxic elements? Or even can we design new materials by substituting atoms which are better? And when you want to do this, you have a number of challenges, which are challenges coming from the combination of high throughput, so running thousands or hundreds of thousands of simulations on HPC, so high performance supercomputers. One is that you have to run workflows, and you have to write workflows, and you have to have a robust infrastructure to write these workflows and run them. But then once you run, again, hundreds of thousands of simulations, you have generating a lot of data, and you want to be able to organize it in a way, not only which is easy for you to do research and search for information, but also eventually to give it to someone else and they can understand what you've done. And most importantly, actually was one of the first things we really wanted to do when we developed our platforms was, can we also ensure that once you have this kind of gigabytes or terabytes of data with millions of files, someone else not only can understand it, but they can also reproduce what we did, which seems easy, but it's not even, it's of course a very hard challenge for experiments, but even for simulation, as I will kind of try to hint in a moment, is not so easy. If you go in a paper today and you try to reproduce a simulation, very often some of the parameters are not mentioned at all or kind of not clear enough because you would have a text file in the supplementary information with methods, but it's typically not enough. And so how do we address this issue of reproducible simulations? The idea we started from is an idea which actually comes from what's called the open provenance model, where essentially any action you do in specific context, any simulation you perform, you can imagine as a black box with some data inputs, crystal structure coordinates, where the atoms are, what you want to predict, some numerical parameters for your simulation, the size of the basis set, etc. And this black box will generate other data. Can, properties, can move the atoms and give you better positions, can do forces on atoms, etc. But you can imagine this is very general, right? Any simulation you do, this has the same shape. And now the idea is that any output data can become the input to a new calculation. And so what you end up when you actually do research, when you do simulations, you end up with a structure which is that of a directed acyclic graph. It's directed because you go from data input to simulations to data output. And it's acyclic because an output cannot have been the input to the same simulation. You're already generating new information. And what I'm trying to convince you here is that if when you run your simulation, you also store this kind of metadata, not only the single inputs and outputs of each calculation, but also the full interconnection of them, you end up with something which essentially already encodes all the provenance, so a history of your data. You have a published result. You can go back in the graph. You can see how this was generated, with which input, but also for this input, in this case, the position of the atoms, this was not something I typed in because I imagined them, but really was the output of another calculation which optimized these positions with some parameters, some approximations coming up from an initial database. So the idea is, can we store this information and how difficult it is? And this graph looks pretty simple, right? You could say, okay, I can do it. But in reality, the real simulation we run, I would say the simple simulation we run look more like this. And I say simple because, for instance, what I see on top is one material, one property. Okay, this is one electrolyte where we're studying, for instance, in this case, solid state batteries. And we want to study how easily, or the conductivity of lithium through the electrolyte. And no, if you zoom in, this is an actual graph or an actual simulation, which was automatically tracked by our software, which I mentioned in the next slide. And this is not more complex than what a person who's experienced in the field will do. You really have to take some input file from somewhere, do some initial analysis, pre-processing of the file, do initial structural relaxation, and then run molecular dynamics to measure how this flows, this lithium flows, and you typically do in multiple steps. And so you see the complexity of doing this, even if you want to do it, if you want to generate this data and then publish it, it's just almost impossible to do even if you want to. It would take just too much time after you publish your paper. And then if you take many materials or many properties, you end up with databases, and this is a graphical representation of an actual database. So we are showing here only links between nodes. It's not even a high throughput, it's really 500 materials. Okay, that's how it looks like. So my message is, unless you have a tool that helps you track this automatically, it's essentially impossible to really make simulations reproducible if you start running hundreds or more, where workflows are not just one job, but you have a lot of steps. And so to address this, what we have developed in the context of Marvel now is in its third phase, so we are year 10 now, but we started so almost 10 years ago with the software. It's really a platform, a Python open source software, which is called AIDA, which essentially allows you to take care of simulation. You ask AIDA to run simulations for you, and it will not only run them on supercomputers, but it will also track all these graphs for you automatically. And it has a workflow engine, which I mentioned in a couple of slides. It automatically, since we run simulation, the simulations are very expensive, they run on supercomputers. It automatically knows how to connect to supercomputers, run there, wait for the jobs to finish and retrieve the results. Automatically track the provenance, and also is very flexible. We didn't want to design a software which was for our code or our application. This really is very general. And essentially, you can use AIDA with any software which has a command line interface. You write a text file, you send it, and you get back some other information. And as you see, we have what we created a few years ago, a registry of all plugins that people have been developing, not only us. And you see nowadays we have essentially almost 90 GitHub or Git-like repositories. You will learn later if you don't know what GitHub is, and which include support for over 130 different codes. Admittedly, now these are still mostly used in our community because it's where people know us and also as a kind of community we know, but we also have already applications going a bit beyond our application. We start having applications also in atmospheric research, weather and climate, quantum chemistry, etc. And I will mention at the end also an example going to actually to experiments. If you're interested, I think the slides will be shared, so you also have the references later if you want with the papers where we describe the software. But reproducibility is a key challenge, but then you also want to have this tool not only track it, because otherwise it's just a complex tool. You also want something which helps you run at exascale. And indeed, AIDA also provides you a workflow engine where you can, so if you want the graph, I give you my graph, it's a log file, it's a history of what someone else did in the past, which is useful to reproduce that very specific calculation, which is good for science, for reproducibility, to make sure that the result is correct. But in reality, you want typically to run something new, right? You want to do new research. You want to take maybe the same material and change approximations and do a better calculation. Or you want to take the same workflow and run for new materials. And so what we also provide is a workflow engine, which given an input, will not only run the workflow for you, but also automatically keep track of the provenance. And the important thing is that for our field at least, most of the simulations, as I mentioned, are a lot of complex steps. In a relatively simple one, as you see, the graph looks already pretty intricate. And there is a lot of expertise which has to go in there to choose a number of numerical parameters. And PhD and postdocs come in the group, they spend maybe 6 months a year, they become experts, and then they know how to do this. What we're trying to do is to write workflows where most, if not all of these parameters are automatically chosen, because either we did studies independently to know which parameters to choose, or because the workflow can automatically detect the right parameters. So eventually the goal, which I'm not going to describe here, but something we also are addressing is on one side be able to run hundreds of thousands of the simulations automatically, and you want them to be very robust. If even 1% fails, you would have thousands of simulations fail, and you have to take care of them. But also to make them very easy, for instance, also for an experimentalist. An experimentalist may want to get this information. In this case, this is called a band structure. If you never saw it, doesn't matter. But given a material, it's very important because it tells you how electrons behave in the material, how light might interact with the material. And people want to look at this if you come from the field. And now even an experimentalist who is looking into this material might, in a few clicks, essentially get the information and understand, better interpret their experiments maybe. And just as maybe it's more advertisement this, but just to show that in the end, a lot of work, and I'm saying this because really it was a lot of work for us, was to achieve high throughput performance. It's not only storing this information, but also being able to really run tens of thousands of simulations at the same time. And to prove this, a couple of years ago, we were given access to probably the largest now supercomputer in Europe, LumiC in Finland, which is also partly owned by Switzerland. And we were given during the test phase in the CPU-only partition full access to the full machine. So you have to imagine this is a 1,500 nodes, almost 200,000 cores. And for 12 hours, we were able essentially to fill the machine with all the jobs. After half an hour, we were essentially using the whole machine, the green bar, and compute over 12 hours, 15,000 materials, properties for 15,000 materials, computing over 50,000 DFT simulations. Just to show that, in the end, we need tools like this if you want to go to the scale, and we need tools also in workflows to ensure reproducibility. And at the scale, it would be almost useless if you were to share just raw files. We need to have something which allows us to understand what we did and have other people understand it. So the first part was about workflows and to show a bit what we've been doing. The second part now is more about data repositories. And also here where we show what we've been doing and describe a bit something hopefully more interesting for everybody. And then I will try to put the two together to try to motivate why the two together can give advantages to research or speed up research. I will specifically start from the example of Materials Cloud, which is a web portal. These are address, which is been designed by us. We maintain in Marvel. We have a number of sections. Some are more educational. There are videos, tutorials, educational material linked in a very interactive way. And then there are a number of other sections. One is more like giving access in the web to these simulation tools, which I'm not going to discuss today, but if you're interested, I'm going to be here around for lunch. And then I will mention more like the 3 sections, which we call Discover, Explore, and Archive, which are more about making data fair and published and accessible. Let me start from maybe the most general one, which is the archive, which is in principle nothing else than a data repository. Okay, so as I was mentioning before in my comment, when we started, we didn't want to do it. We said, okay, we just try to use Zenodo, but it wasn't possible to find a way to just put a lot of data there. So we developed our own using their software. So we are actually using under the hoods the Invenio and Invenio RDM software that CERN develops and uses for Zenodo. So we just redeploy it and customize it for our needs. And what is Material Scale Archive? It's a discipline-specific repository. It's a decision we made. We only accept data from our discipline, material science, and typically simulations. Now we're extending to experiments. And I will mention later why this can be a benefit to have also discipline-specific repositories. And what it does, you have your paper, right? Now you have requirement from SNSF, but also strong recommendation in general to take your data from your paper and put it somewhere so other people can fully reproduce your paper. So what you do, even if you don't use AIDA, you just go there, you can upload your files and it's standard metadata, title, files, etc. And we give a DOI for this, thanks to the ETH library, which is the provider from DataSite. And we guarantee, thanks to partnership with CSCS, the Swiss Supercomputer Center, that the data is going to be there for at least 10 years. And the important other difference with respect to other repositories, which you can do because it's a discipline-specific one, it's a moderated repository. What does it mean? It means that you submit a data entry, so you can go and get an account, it's for free. Once you submit it, a human, a person will read it, and typically within a couple of days, and reply to you, either saying, fine, we publish it, or saying, really, we can't publish it, it's really out of scope, or giving recommendations. So it's not a peer review, okay, it would just take too much effort to have one person peer review everything. The idea is really this is a repository for research, which should be anyway be peer reviewed in a journal, but it's more like a quality check, okay? So people who are moderators, there are a few active ones plus a few backup, are people who have a background in physics and material science, so they understand what's going on. Essentially, if they can't understand what the files are, they would tell you, oh, there is no README file, right? For instance, or this format, it's not clear how I open this format. Maybe why don't you use an open format, no? So it's really a more quality check and helps improving the overall quality of the repository. I think with the added benefit that people come in here and wanted to submit a new entry. So I guess if you were to submit, I guess you would open a few random ones and see how they look like. So I have the feeling that this is really going to help the overall quality of the data set, because new users will see how other entries are done and existing users will have learned. And when you do new publications, the data is much more accessible. It has a cost, of course, and I was saying before, probably that the human part is the higher cost of this. But these are one of the interesting things of having a discipline-specific repository. You might have things already which start just by the fact they are discipline-specific, they're higher quality in general. By itself, I'm not going to spend much on this slide. I mean, it's a standard repository in a sense. You have a submission form, you log in, you can put your keywords, fields, license, etc. Once you publish it or approve it, you have a user interview, you can see your own entries, and then you can also, and for this you need your account. But then if you have not logged in, you can anyway see all the data because it's fully public. You don't need any account to see other people's data. And once you publish it, a page would look like this. You have, again, usual things, title, author, affiliations, the DOI we provide, publication data, a citation string, a description, which is essentially an abstract. And apart from this, which I discuss later, a list of files, but for every file, you have a short description. And typically, we recommend also to have a global README to explain how things done. As was already mentioned also in the slides before by Valeria, we have limits. And again, it's because we wanted to put some kind of limits in order to avoid it to get 20 terabytes and we don't know what to do. Even if at the moment, again, that's not the problem. The whole thing after 5 years is 1 terabyte. So no, just to give an order of magnitude, which is also actually something we push in our research strategy, in our data management plans. sometimes we can do a bit of effort as a researcher to decide how much data you really want to store in the long term, and how much data you can reproduce easily or cheap, or in an easy way in a general sense. It can be cheap, or it can be because it's not too much CPU, or it can be easy in the sense that it doesn't require a person spending 2 years to understand how to do it. No? And so it's always a balance, because the costs are small, but there are still some costs. So if I just dump everything my code produces and I have a petabyte of data, I can put it there, but maybe it's irrelevant. So it's always a balance, and having limits also helps people think about, okay, maybe I should reduce it. These limits, by the way, are lifted for people from NCCR Marvel and for a number of other projects which contribute to the platform. So NCCR Marvel researchers don't have these limits. These limits we decided to open this to the world. So we wanted to get a limit to people who essentially get it for free. And that's why we have this limit. Something which happened in the past few years in the community, that a number of journals or institutions or funding agencies like SNSF started to compile lists of recommended repositories. Material Scout is in 3 of them at least, so I just put it there, not much for advertisement, but really because I wanted to give this message that these lists are extremely useful. If you're not from my field, let's say, maybe you don't care about Material Scout Archive, because you can go there and see for your discipline what are recommended repositories. And these recommendations, I guess every institution does it in a different way, but I think SNSF had a survey and checked statistically what people did, at least from what is written. You can correct me if I'm wrong. But for when we applied, in a sense, for the Nature scientific data, there was a kind of a long questionnaire where they were asking about the terms of use, how we guarantee sustainability, how open are we, how open are the metadata formats with which we share the titles and the OI, etc. So things which are in this list typically are already kind of high quality. It's not just a person putting files in a repository. And this is very useful. And of course, this list also includes a number of generalistic repositories, which were already listed before. I just put 3 screenshots, just some which are known, which I think are extremely important. It's important to have these repositories. And in many cases, if you really don't know what to do, you just have your data and your scripts to generate figures, your raw data, etc. You want to publish it. You just go in one of them, you get a DOI, you cite it in your paper, and at least your data is public. But if you find a discipline-specific repository, typically it will give you some added value. One, in our case, we have moderation, for instance. Typically, it's a smaller community, but in the end, maybe you care about your published papers go to your community. Maybe it's okay if other people read it, but you care that they are visible and advertised in your community. So having a smaller repository that your community monitors helps increase visibility. But also typically they might have features that enrich the data. I think before in one of the comments, I guessed, if you have repositories, I guess for microscopy, you have specific metadata you can show or specific visualizations. In the same way, later I'm going to show in a few slides how we enrich our data in the case people have been using AIDA. And that's exactly my kind of last part of my talk, which is when you now combine reproducible workflows with open data repositories, what is the added benefit? And I want to show one example from my own research, something we call MC2D, or Material Scout Two-Dimensional Database. You have here also URL. And this was published in Nature Nanotechnology, it was 5 years ago now. And the data is fully open on Material Scout Archive. And I want to show you how putting together the fact that the simulation will run with AIDA and an open repository will increase visibility and accessibility to our results. So really going to the A of FAIR, accessibility. So maybe just before I go, what is this project about? So at least you know. So in Nature, there are a number of materials which are layered. Probably most of you have heard about graphene. There was a Nobel Prize in 2004. Graphene is the layers which compose graphite. So when you write with a pencil, the pencil writes because this very thin layers, a few atoms thick of graphite detach and remain on paper. And this is when you get a single layer, you get exceptional properties of your material. And in 2004, there was the Nobel Prize for graphene, which was obtained by using a Scotch tape technique, very kind of trivial apparently, but now there are more advanced techniques also. And until 5 to 10 years ago, experimentally, there were probably, let's say, 50 known layered materials. But they're super interesting. They're a huge surface of very good fractalysis. They can have a very interesting fundamental physics properties, like topological properties. So it's very interesting to know if there are more. So what we did is to start from bulk, so data, as I said before, databases of three-dimensional materials. Essentially, people go in mines, find a material, do spectroscopy, and then understand how atoms are arranged. And we said out of these databases, which typically have 100,000 materials, are there others which are layered? And we started with geometrical algorithms. We look at where atoms are and there is space between atoms, but then we go into actual simulations to measure the energy to actually detach these layers. And in the end, we result with a database with now has about 2,000 materials, which all coming from experimentally known bulk materials. It doesn't mean they will always be able to get a single layer, but we start. It's interesting because there are materials you can get in the lab. And just to mention the story, after this was published, we look into properties. One material was extremely interesting from some topological properties, some kind of fundamental physics properties, which are very studied nowadays in my field. And we went back into the paper where the material was discovered, the 3D material. And this was discovered in a mine in Brazil. It's called Jacutingate, measured in Czech Republic and then left in a shelf because they were happy. They published it. Nobody cared. They didn't know what to do with this material, right? And then my colleagues went to them and said, look, we think this material is really important. Do you have it? And they still had it. So they could ship it to other experimental colleagues. And now, in the past 3 or 4 years, there have been tons of papers on this material because indeed it showed to be kind of very interesting as we had predicted. So again, another example of open data, these people published the structure without really knowing why it was relevant. And after 10, 15 years, we discovered that it's interesting and an example of why open science works. Anyway, going back to my example, what we did with this. So first of all, we ran all of this with AIDA. We published the data in the archive. We made a simple entry, authors and files. And among the files, we not only put a zip file with things in our community people can understand, but also put a full export of this big graph I mentioned. So a person using AIDA would be able to just import it and look at it and get the final published result and go back and see exactly how we computed any property. In addition, again, as you can imagine, I guess none of you would know how to actually look into this file. I give you this 5 GB file, you have no idea what AIDA is, you have no clue. So what we did is to publish it in what we call the Discover section now, which is what we use for curated datasets. So now we take each of these 2,000 materials and we make a page, a web page, so you can just go here and click around. And for each property, we summarize the important things a person who understands a bit of these materials would know what is the geometry and the symmetry of this material, the band gap, so if it has substrate or not, if it's magnetic, etc. But now, as you see, since we did it with AIDA, we could make these little icons. This is the logo of AIDA, which are links which make you jump directly to the specific node in our graph where this specific piece of data was computed. So you see this one, all these numbers which were computed, we can click on them and you jump in what we call the Explore section, which is essentially a graphical interface to really browse through your graph, or the graph we generated. This is a little animation we'll show in a moment, but just to explain what's going on. This piece of data was computed and published, and it's in the supplementary material as a PDF. We have a PDF of a few thousand pages probably. But again, not very interesting unless you know how it was computed. You click here and you will see what GitHub is later. But for those of you who know, the analogy I like to make is the following. Like Git allows you to keep the history of your source code, of your files. GitHub or GitLab help you visualize this in a web browser. No? You can go and look at the history in a very easy way without having to type things in a terminal. Materials Cloud Explorer is a bit the same for AIDA. So AIDA keeps track of the history of your data, and Materials Cloud Explorer allows you to just put the data there and browse through it and visualize it. How does it work? So let's say I want to know how this band structure was computed. I click here, I get into this page. This is my node, and I can see this as an output. Essentially, some calculation that used this as an input to do post-processing. But this was generated by something which you probably don't read, but it's called Quantum Espresso. It's the name of the code we used to actually generate this plot. And if I now click on it, I can not only visualize this object in an interactive way. It's not anymore a PDF, but it's really something I can zoom, etc. But I can click on the calculation that generated it. I can see all the inputs and outputs nodes as they were calculated by AIDA, but I can also look at if I'm an expert, I can look at the raw text file, which was the input of this calculation, and the raw output. So if I'm a person who knows this, I understand what these files are, I can copy paste and run them again. And again, I can say, okay, what was the input structure of this? Well, I find the correct node, I click on it, and I can visualize here the structure in 3D. I can download it, but again, I can see this was used by 3 calculations. One is the one we reclaimed, but this structure was also used for something else. But also this structure was created by something else, and I can keep browsing my history graphically in the browser, even if I don't know AIDA. And so for us, this is the way in which we make our research accessible. It's really, anybody who essentially, maybe like this 10-minute introduction to know what we're looking at, they would already be able to at least look at what were the raw input files and the raw output files from our simulation. And since this is fully tracked automatically, it's very easy for the person who runs it. And it's also very easy to publish it, because then you can just ask AIDA, give me a big file and publish it there. Creating this from a file is automated. So once you have an AIDA file, this section is automated. Of course, as you can imagine, making a discover page requires effort. So we really wanted to make the database public. So we had a person who developed this, and this requires a bit of effort. This cannot be really be made automatic, as you can imagine, because you have to decide what are the important properties and how to visualize it for your community. But I think there is no way around it. And the final comment on, so the goal of this was to show having a repository which is a bit more specific to your discipline allows, in this case, for the case of reproducible simulation, to have automatic links which generate this kind of interfaces for you. Or it could be in a case of data where there's a very clear metadata standards to visualize it in a more effective way. So that's why if they exist, it's good to use them. And the final comment is also that since we also come from research, right? So we are very interested not only in making data fair, but also to simplify people's life when they want to use these tools to write projects. And so we took inspiration from existing templates for data management plans for SNSF or for H2020 Europe. And we enriched these templates with sentences which already explain how things are done if you deposit your data on Materials Cloud Archive, or if you use AIDA. Then in this case, you just take this template and you can adapt your sentences. So this, I think, helps a lot when you have to write a DMP, because maybe you don't know how data is stored, and we can explain there, okay, if you put data on Materials Cloud Archive, this is stored by 10 years by collaboration with CSCS, et cetera, et cetera. Okay, in the last 3 minutes, I wanted to show like the future or where we are trying to go now. And this is actually a collaboration with the group of Professor Corsi Battaglia at EMPA, and there is Nucorn here in the audience who is part of this group. We're collaborating to go a step further, which is not only simulations, but also experiments. And in their lab, they do, among other things, experiments with batteries. They have robots to assemble batteries that they coin cells, put the electrolyte inside, close it, and then they can do cycling experiments to see how well the battery performs. And nowadays, these are quite their research, I'd say, they're really making this very, very automated. And the question is, can we use workflow engines like AIDA with provenance tracking to actually track the provenance of experiments which are already robotic? And that's what we are doing in this project, which started a year ago, and now we are continuing, where essentially we are providing, on one side, a graphical user interface, which again, I didn't discuss, but just imagine, it's a graphical user interface where the experimentalist can run batches of batteries. So I want to run 32 batteries with these different compositions. This will run an AIDA workflow under the hood, but this AIDA workflow will not run a supercomputer calculation. We actually submit an experiment to this robotic platform. And in the end, in the browser, already the user will be able to see the results of their experiment. And we are doing 2 things. On one side, we are a project funded by one of these open research data projects by the ETH domain to investigate how we can make metadata interexchangeable between simulations and experiments. And we use this as a kind of a test bed. And this might look trivial maybe, or maybe not, I don't know, but I tell you one example why it's not trivial. If you take a calculation and I want to simulate a silicon sample or gold sample, let's say a piece of gold, I put the positions of gold in a file. I can run 1 million simulations on this file, nothing happens. Now, this file is always the same file. If I have a gold sample, I can do measurements which can destroy it or damage it or anyway change its history. So already it's not obvious how I map the concept of a sample to a concept of an input file. And even there, there is not a one-to-one, there's a many-to-many relationship. Now I can have, of course, many gold samples, which in the end are well represented by the same inputs. Or I can have the single gold sample, which maybe has microstructure and I want to do multiple simulations. So it's really a many-to-many simulation. So it's a non-trivial metadata issue, which we're trying to address. And the other thing is really going toward, as I mentioned at the beginning, autonomous laboratories. Because now, if I can ask an experiment to run automatically, and I can ask a simulation to run automatically in a very robust way, it doesn't crash. Now I can try to understand if some genetic algorithm, for instance, can ask to run some batch of batteries, look at the results, maybe ask some help from experiment for simulations, and decide what is the next generation of batteries to run to, for instance, optimize the lifetime of a battery, how many times I can discharge it. And that's really the kind of the goal where in my group in PSI, we are trying to go with all what I've presented. And the goal of this ORD premise, as I mentioned, this premise of this ORD project is really not only to design the metadata, but also to make it fair from the design. So you don't have, at the end of this process of this research, make it fair and publish it, but everything is ready to be published in a way. With this, I want to thank all the people who have been part of the team or are part of the team of AIDA Materials Cloud, plus a number of contributors of the project, which has actually made this possible. Of course, I couldn't have done it alone. And all the funding, in particular Marvel, but also we had a lot of funding from the H2020 Center of Excellence, MAX. Now we're not part of it because Switzerland is out, but no, we're still collaborating a lot with them. And ETH board, Swiss universities, and a number of European projects. And so to wrap up, I hope I managed to convince you, and I hope some of this was useful for you. On one side, if you want to run a lot of simulations, you need something to help you track the provenance automatically. Otherwise, you will not be able to explain what you did later. There are not many repositories. I just mentioned a few. Generally, it's good, but if you find one which is discipline specific, it might have a lot of added benefit. And there are lists online which help you find if there is a repository for you. And finally, if you combine the two, it really can help increase, in the end, accelerate research. And even if you want to look from a very personal point of view, if you publish your data and people can use it, they will cite you. So in the end, no, actually, one of my most cited papers is a paper in which I took my little simulation and I put it online in a web tool. People go there and they get maybe a few citations per week. I'm very happy. Just because in the end, this software was not particularly complex, but if it's on the web interface, you can put a file, drag it, and press a button, wait a second and get a result and put it in your paper. People find it useful and they cite you. So even just making these little things can help even your personal career if you want to think only about that. Thank you for your attention.
Any question?
This was a great talk. Thank you. So if I got it right, you created your own disciplinary specific repository and also this AIDA software. And you recommend that maybe other communities do it if it's missing. But my question is specifically, so Marvel is now 10 years or so going, so it will not exist for too long. But what is the deal you have in order to maintain this? What is the scalability for the whole community? Because it may grow if it's very actively used. And how do you see this model actually being maybe a blueprint for other institutions?
So it's a very good question. So I'll try to answer everything. I will probably forget half of the questions, so we ask you again all the questions. But first, I'm not sure the right idea is to everybody develops their own repository, because in the end, it's a lot of work and there's a lot of potential maintenance burden, because as you say, now we have to maintain this, right? We have designed from the very beginning in a way in which if we really have to, we can phase it out, in the sense that if we decide we don't accept any more contributions, we can convert everything into a static website. It's just be a static website with a terabyte of data. We find somewhere where it can be hosted. We redirect the DOIs there, and we almost forget about it. And hosting a terabyte these days is almost trivial. I mean, almost trivial. In principle, one can move it to some other repository. Nevertheless, I think so I would really encourage people to try to see what's around. Then there are, as I said before, a number of practical issues. If you really have a lot of data and you find nobody who can really host it, what do you do? And especially now I'm in PSI, these facilities create a lot of data, microscopy, spectroscopy, etc., and they have to have their own repository, right? So just because they're petabytes of data, they have to put it somewhere. So it's not a general recommendation to make your own. Actually, ideally, you shouldn't make your own. You should try to find someone else who does it. Excellent question about sustainability. Now we're exactly in the last phase of Marvel, which is exactly a focus about sustainability. And there is a lot of political thing you have to do in a sense to make it happen, because it happened thanks to our director Nicola Marzari. In the first 8 years he managed to create connections, in particular with PSI, and actually the fact probably I'm now group leader is part of this sustainability, because now there is a new division created 1 year ago on simulation at PSI with different labs, and my group gets funding now, matching funding, let's say my salary and 2 senior scientists' salary, tenure track, to match 4 postdocs for 4 years for the last phase of Marvel, with the idea that then PSI will continue. Okay, so this group now so there are 3 new people, me and 2 more, which will be permanent, hopefully, if my tenure track is approved. And there's a way to sustain it, because then this group will be in charge of maintaining it. And no, PSI, that's the interesting thing. Universities are more, especially in my experience in Switzerland and EPFL, are driven by research. So there is a professor with his group, the professor retires, people disappear, and that's a new group. Facilities have a completely different mindset. Facilities have things that have to be there for 50 years. They have this mindset, they have people, senior scientists, senior people who are in charge of the machines, just fixing them or improving them. So the goal, the theme, if you want, of Marvel, that what Nicola Marzari says is we as a scientific community, we put millions and millions into these physical facilities, these experimental facilities, synchrotrons. We can put a fraction of the cost into making a simulation facility, which is much cheaper, but requires a bit of this vision that is not something you can write a code, put it on GitHub and forget about it. You have to have a team of people maintaining it. So the hope is that PSI and the group and the laboratory and division in general will be the place in which what Marvel has created can exist in the long term. There was a final question which I forgot, as I mentioned, or maybe I replied to everything. I don't know.
Yeah, maybe scalability. So we talk about negative questions. But let's say everybody's going to be.
Yeah, that's a very good point. I would say for me, closing it wouldn't be actually a problem because nobody uses it. It's probably the problem because there's no funding for people maintaining it, because it's a website. It has to be there 24 hours a day, no interruption. So you need the software engineers in the end who understand it and can fix bugs, update security patches. There are a lot of technical things to be taken care of. It is increasing. So in the past 5 years, I've seen a kind of a steady increase. We now have 1,000 users from 0, 10, 50, 100 every year. The good thing of these repositories is they're quite scalable, because in the end, one thing we might decide at some point to drop is the moderation. That's definitely one thing in which you need a person, and it's hard to scale. You get 2 times more entries, you have to moderate 2 times more. On the other hand, if the platform is robust and that we are really now migrating to the new version of InvenRDM, trying to minimize the customization we do, we really use the stock software that CERN is developing. As long as CERN develops it, the amount of effort is maintaining the website. But if you receive 100 or 200 or 1,000 entries, the cost to maintain it is relatively the same, more or less the same. I mean, it scales very little with the amount of entries we receive. So in this sense, that's why we are relying a lot on this open software and well-maintained software, which again is behind Zenodo, so the hope is going to be there for some time, because we'll reduce the amount of custom software we have to maintain. And it's a very scalable approach in a sense.
Any other question? Okay, so I have a last question, Sarah. I see you tell me to move on, but so you created, basically, you designed Material Cloud because you didn't find what you need was out there for archive, discover and explore, or explore and discover. So can it be, can we adapt it from life science, for example? And it will be also a great way to show that what you created is actually transferable to another discipline. Yeah,
so let's say it depends, because there are many pieces now. So I would say the archive, yes, definitely. Again, since we are using in the end, in Venio, we learned a lot how to customize, and also we started a few years ago. Now in Venio is also developing in a more modular way, so it's easy to customize. And in the new migration, we will, I think, understand how to make a lot of customization. So this will be also open, and hopefully another community who really has to develop their own, because maybe an example, we have 50, 100 terabytes of data, you know where to store it, you need to put it somewhere. You can just adapt the work we did. It's not going to be zero work, but it's going to be much easier than for us. That's definitely something which I see as very reusable in a way, at least the know-how and even the code. AIDA by itself is open. As I said, we are now extending to more disciplines, including disciplines which have data requirements which are very different from us. The code can already be used. If you have a code, you could use it and have to make your plugin to let AIDA know how to create the input and parse the output. But of course, it's designed around the amount of data we typically transfer. In atmospheric or meteo weather, they have maybe huge petabyte things move around. So we are now working to make it more scalable, but the idea is that in a couple of years, this will be ready. So if people are interested in a different field to use the idea, they can take the code, try it out. There are very good, I spent a lot of time for training, documentation tutorials. Like you can download a virtual machine, a tutorial we typically run every year is fully self-contained. You can do it yourself. As long as you know a bit of Python, you can follow the tutorial, spend a couple of days and go to the point you can write workflows. So we try to make it very open. Of course, there is a barrier, right? Because it doesn't cost for free in the sense that you have to understand how AIDA works and put it in front of your actual software. And as was mentioned before by a number of people, I think by Valeria, it's really also a matter of, I think, mindset. If you get young researchers, and speaking in my field, a PhD student or even a master student, they're super happy. They find it's Python, they love Python. Wow, let's do it. And they're happy. If you take a person who has 20 years of experience, they have probably designed their own scripts. They don't really care about changing because for what they do, what they bash scripts or whatever they have works fine. So we realize that's not probably the target audience. Probably if we already manage to capture the young ones in a generation time, let's say this is how things work, I think people will go more into this direction. Not necessarily AIDA, but this. Material Scout itself, I mean, it's a website, so it's very specific to the kind of research we do, but I think many people have their own websites, so this will be, we have some technical aspects we can share, but maybe that's a less how to say this, really, we needed to share our data and we did it, but Archive and AIDA, I think, are very potentially broad.
So we need to move on. Thank you again for your talk, Giovanni.